Today we're going to prove the following formula, that determinant of A times B is equal to determinant of A times determinant of B. So here A and B are two square matrices of the same size. The proof of this formula will be split into two cases. So in case 1, we will assume that determinant of A is equal to 0, or determinant of B is equal to 0. And under these assumptions, we're going to prove that determinant of the product is also equal to 0. And in case 2, we will assume that determinant of A is not equal to 0, and determinant of B is not equal to 0. Along with matrices A and B, we're going to consider linear transformations that correspond to these matrices. So let T and S be linear transformations from F to the N to F to the power N, so corresponding to A and B. So this means that for V in Fn, so T of V is defined as a product of a matrix A with the vector V, and S of V is defined as a product of a matrix B with vector V. So if we're given two square matrices, then they give rise to linear transformations from Fn to Fn. We recall the following theorem that relates the properties of a linear transformation to the determinant of its matrix. So theorem. So let T be a linear transformation from Fn to Fn with matrix A. So then the following conditions are equivalent. One, determinant of a matrix A is not equal to 0. 2, T is bijective. 3, T is injective. So keep in mind here that T is a transformation from Fn to Fn. So these dimensions here are equal. So in this situation, bijectivity is equivalent to injectivity, or it is also equivalent to surjectivity. Now let's consider the following proposition. So suppose S be a linear transformation from U to V, and T be a linear transformation from V to W. So these be linear transformations. So then the kernel of the composition T composed with S contains the kernel of S. So this will be property 1. And property 2 is that the image of the composition T composed with S is contained in the image of T. So let us give a proof of this proposition. To prove property 1, let's recall what is the kernel of S. So this is the set of vectors V in Fn such that S of V is a zero vector. So suppose V belongs to the kernel of S. So here we need to show that kernel of S is a subset of kernel of the composition. So thus we need to prove that if some vector belongs to the kernel of S, it also belongs to the kernel of the composition. So if V belongs to the kernel of S, by definition of the kernel, this says that S of V is equal to 0. But now let us compute what is T composed with S applied to V. So this is T of S of V. But S of V is equal to 0 because V is in the kernel. So this becomes T of a 0 vector. But we know that for any linear transformation, T of 0 is equal to 0. And so this tells us that V belongs to the kernel of the composition T with S. And this shows that any vector in the kernel of S actually belongs to the kernel of T composed with S. Now let us prove the second part of this proposition. So here we need to show that any vector that belongs to the image of the composition actually belongs to the image of the second transformation. So let W belongs to the image of the composition T composed with the S. So what does it mean? So this means that W is an image of some vector under this transformation. So this tells us that there exists vector U in the space U such that W is T composed with S applied to U. So which is the same as T of S of U. Now we set V to be S of U. So then what we get is that W is equal to T of V. But this means that W has a pre-image in the space V under transformation T. And so this tells us that W belongs to the image of the transformation T. And now we proved that any vector in the image of the composition also belongs to the image of the second transformation. And this proves the second relation. Now let us start proving this formula. And we will begin with the case 1a is when determinant of A is equal to 0. So what we need to show here is that if determinant of A is equal to 0, then determinant of the product A times B is also equal to 0. Our theorem about the relation of the determinant and the properties of transformation can be also reformulated in the following way. So if we negate everything, then we get that the following four conditions are equivalent. That determinant of A is equal to 0 is equivalent to the fact that the corresponding transformation T is not bijective, which is equivalent to the claim that T is not injective, and equivalent to the claim that T is not surjective. Now let us build a chain of implications. So if determinant of A is equal to 0, this implies that T is not surjective. So which means that the image of T is strictly smaller than Fn. But what we proved here is that the image of the composition is contained inside image of T, which is strictly smaller, so it contains an Fn, but not equal to Fn. And from here, so we conclude that the image of the composition, right, so which is even yet smaller, right, so here we could have equality, but not here, so which is could be even smaller than image of T, so this is not equal to Fn. So this tells us that this composition, T composed with S, is not surjective. And by this statement, this says that the matrix of T composed with S has zero determinant. But what's the matrix of this composition? The matrix of that composition is A times B. So this has determinant 0. And this proves this formula in the case when determinant of A is equal to 0. So if determinant of A is equal to 0, then determinant of A times B is also equal to 0. And so the determinant of the product is equal to the product of determinants. Now let us consider case 1b, that in that formula, determinant of B is equal to 0. If determinant of B is equal to 0, this tells us that S is not injective, which says that the kernel of S is not equal to a zero vector. So there are non-zero vectors in the kernel. So this is equivalent to injectivity of linear transformations. But what we proved here is that the kernel of the composition contains the kernel of S. So if S contains non-zero vectors in the kernel, then the same is true for the composition. So this tells us that the kernel of the composition T with S contains non-zero vectors. And so this tells us that this composition is not injective because it has a non-zero kernel. And if we have a transformation which is not injective, this tells us that the matrix of this transformation has determinant 0. And the matrix of T composed with S is A times B. And so this tells us determinant of A times B is equal to 0. And we proved that if determinant of B is equal to 0, then determinant of the product is also equal to 0. So now, so we proved this formula in the case when either determinant of A is 0 or determinant of B is equal to 0. And it only now remains to consider the case when both determinant of A and determinant of B are non-zero. Let us recall a relationship between elementary row operations and the determinant. So here we have elementary row operations. So let us list their effect on determinant. And here let us write down what is determinant of elementary matrix. So recall, to each elementary row operation we associate an elementary matrix. Now we have type 1 elementary row operation. When we add to a row a multiple of another row, and its effect on determinant is, we know that determinant does not change when we apply this elementary row operation. Now let's recall what's an elementary matrix. So elementary matrix is a matrix obtained from identity matrix by applying given elementary row operation. If we are talking about elementary row operations of type 1, then determinant of identity matrix is equal to 1. And if we apply type 1 elementary row operation to identity matrix, the determinant doesn't change. So this tells us that in type 1 elementary matrix has a determinant which is equal to 1. Now let us look at type 2 elementary row operation. So here we take one of the rows and multiply it by a non-zero constant k. So the effect on determinant is that determinant gets multiplied by the same constant k. So the corresponding elementary matrix is obtained from identity matrix by multiplying one of the rows by a constant k. And so what we see in this case is that determinant gets multiplied by k, and so the determinant of elementary matrix of type 2 is equal to the value of this constant. Now finally we have type 3 elementary row operations. So this is when we switch row I with row j. And the effect on determinant is that determinant switches sign. So if we take identity matrix and apply elementary row operation of type 3, so this means that we switch two rows in the identity matrix, then determinant switches sign, and the resulting elementary matrix will have determinant which is equal to -1. And we have a relationship between elementary row operations and elementary matrices. So we know that applying an elementary row operation to matrix A is equivalent to multiplying A by corresponding elementary matrix on the left. So this means that if we consider the product E times A, then this product is equal to the result of applying the corresponding elementary row operation to matrix A. From here, we obtain the following proposition. So if E is an elementary matrix of type 1, 2, or 3, then determinant of E times A is equal to determinant of E times determinant of A. Well, we prove this proposition by considering type 1, type 2, and type 3 elementary row operations. So if E is an elementary matrix of type 1, then we know that multiplying A by E is the same as applying type 1 elementary row operation. But type 1 elementary row operation does not change the value of the determinant. So determinant of E times A for type 1 operations will be equal to determinant of A. But the determinant of E is equal to 1. And in this case, we get that determinant of E times A is equal to 1 times determinant of A. So likewise, in type 2, determinant of E times A, well, so here the determinant gets multiplied by k. So this means that the left-hand side will be k times determinant of A. But so is the right-hand side, because determinant of elementary matrix is equal to k, so we get k times determinant of A in the right-hand side, and the equality holds. And similarly in type 3, if E is an elementary matrix of type 3, then determinant of E times A. So the determinant switches sign. So the left-hand side is equal to minus determinant of A. And so is the right-hand side, because the determinant of elementary matrix is equal to -1. So we get -1 times determinant of A. And again, the left-hand side is equal to the right-hand side. Let us now prove the following theorem. So if A is a square matrix with non-zero determinant, then A may be factored as a product of elementary matrices. So A is equal to E1 times E2 times EK. Now let's give the proof of this theorem. So if determinant of A is not equal to 0, then so this is actually equivalent to saying that reduced row echelon form of A is the identity matrix. But then, so this tells us that I may be obtained from A by applying a sequence of elementary row operations. But elementary row operations are invertible. So this tells us that A may be obtained from I by applying a sequence of elementary row operations. But we know that applying an elementary row operation is equivalent to multiplying by an elementary matrix. So this tells us that there exist elementary matrices such that A is equal to E1 times E2 times EK times I, right? So here we take identity matrix and we apply elementary row operations that correspond to these elementary matrices, and we obtain matrix A. And so if we can obtain A from I by a sequence of elementary row operations, so this means that A is a product of a sequence of elementary matrices times I. And that's exactly what we had to prove. Let us do an exercise illustrating this theorem. So let us factor the matrix 1, 2, 3, 4 into a product of elementary matrices. So we start with the matrix 1, 2, 3, 4. And we want to apply elementary row operations, then bring this matrix to identity matrix. So on the first step, we say that row 2 new is row 2 minus 3 times row 1. So this gives us the matrix 1, 2, 0, and 4 minus 6, that's negative 2. Then our next elementary row operation is we say that new row 2 is equal to minus 1/2 times row 2. So this gives us 1, 2, 0, 1. And finally, we say that let us take row 1 and subtract from row 1 2 times row 2. And if we do this, then we get the identity matrix. Now we go back. So to get this matrix from the identity matrix, we say that new row 1 is row 1 plus 2 times row 2. And this is actually the elementary matrix that corresponds to this elementary row operation. So here, to undo this operation, we say new row 2 is equal to negative 2 times row 2. So if we multiply the second row by negative 2, then we get this matrix. And here we say new row 2 is row 2 plus 3 row 1. So this is an elementary row operation that will undo this one on the top. And now, if we start with identity matrix and multiply it by elementary matrices of these reverse elementary row operations, so here we will have 1, 2, 0, 1. Next factor will be, so the elementary matrix that corresponds to this elementary operation. So 1, 0, 0, negative 2. And the last elementary row operation will have 1, 0, 3, 1. Then the product of this will give us the matrix A, right? So this will be A, which is the matrix, right? So this is equal to 1, 2, 3, 4. And you can verify that the product of these three elementary matrices is equal to the matrix that we started with. And of course, the identity matrix as a factor on the right may be dropped. So now we return to the proof of our formula for the determinant of the product. So in our case 2, when determinant of A is not equal to 0 and determinant of B is not equal to 0. So we need to prove that determinant of the product is equal to the product of determinants in this case. So since determinant of A is non-zero, then we can factor A in the product of elementary matrices. So this means that A can be written as E1 times E2 times EK. Well, and if we wish, we can put identity matrix here. So for some elementary matrices EI. And the same we can do for B. So determinant of B is non-zero. By the result that we proved, every matrix with a non-zero determinant may be factored as a product of elementary matrices. And here let's call this elementary matrices EK plus 1 times EK plus 2 times ES. And we can also put I here on the right for good measure. Then let us look, what is the determinant of A and what's the determinant of B? This proposition tells us that if we have a product of an elementary matrix and some other matrix, then the determinant of the product is equal to the product of determinants. So for determinant of A, so here we have an elementary matrix times something else. So this is equal to determinant of E1 times the determinant of what remains. But then we can continue this factorization using repeatedly this proposition. And what we get is that determinant of A is equal to the product of the determinants of these elementary matrices. But the same can be done for matrix B. So determinant of B is equal to the product of determinants of the elementary matrices that appear in its factorization. So we have determinant of EK plus 1 times determinant of ES. But now let us consider determinant of the product. So if we have a product of two matrices, A and B, then we can substitute their factorizations. So we get determinant of the following product of elementary matrices. E1 times up to EK times a decomposition for B is EK plus 1 dot times ES, and we can put identity matrix or drop it, right? And then by the same argument that we obtained using this proposition, so this determinant of the product of elementary matrices is equal to the product of determinants of elementary matrices. So we have determinant of E1 times ... determinant of EK times determinant of EK plus 1 times ... determinant of ES. But, so here, if we split this into two groups, then we see that the first group is equal to the determinant of matrix A. And the second group of factors is equal to determinant of B. And so this proves the formula that we wanted to prove. So in case when both determinants of A and B are non-zero, we prove that determinant of the product is equal to the product of determinants. In particular, this says that if A and B have non-zero determinants, then their product also has a non-zero determinant. Well, we already knew this, so we could explain this differently. So if A and B have non-zero determinants, these are invertible matrices. But we know that the product of two invertible matrices is invertible because we have an explicit formula for the inverse of the product using the inverses of the two factors. Let us mention a corollary of this formula. So if determinant of A is not equal to 0, then we know that the matrix A is invertible. So then the determinant of the inverse matrix is equal to the inverse of the determinant of A. And to prove this, so we know that the inverse matrix satisfies the relation that A times A inverse is equal to identity. And if we take determinant of both sides, then we get the determinant of A times A inverse is equal to determinant of identity matrix. But on the left, we now have a formula that says that determinant of the product is the product of determinants. So we get the determinants of A times determinant of A inverse is equal to 1. And this implies that determinant of A inverse is the inverse of determinant of A. Now let us talk about the geometric interpretation of the determinant. Let V1 through Vn be n vectors in Rn. Form matrix A by placing V1 through Vn as columns. Then the volume of n-dimensional parallelepiped formed by vectors V1 through Vn is given by absolute value of determinant of the matrix A. So for example, if we have 3 vectors in R3, then we can span a parallelepiped with these 3 vectors. And so the volume of this parallelepiped is equal to determinant of the matrix where we have V1 as the first column, V2 as the second column, and V3 as the last column. So we form a 3 by 3 matrix. And so if we take the absolute value of this determinant, then we will get the volume of this parallelepiped. The extreme case, when these three vectors collapse into one plane, right, and so this parallelepiped will flatten. So this will correspond to the case when the vectors v1, v2, and v3 are linearly dependent. And so the determinant will be 0 in this case. So we can see that we get 0 volume exactly in the case when determinant of the corresponding matrix is equal to 0. As an exercise, so let us find the area of a parallelogram formed by vectors 1, 2, and 3, 4. So here, let's make a picture. So we have on R2, we have one vector which is 1, 2, and another vector which has coordinates 3 and 4. Well, so here we have, we complete this to a parallelogram. And what we want to do is we want to calculate the area of this parallelogram. So the area is equal to absolute value of the determinant of the matrix 1, 2, 3, 4. So we have a formula for the determinant of a 2 by 2 matrix. So this is 1 times 4 minus 2 times 3. And so we get absolute value of -2. And so this means that the area of this parallelogram is equal to 2. Now let us relate this to linear transformations. So consider a linear transformation from R2 to R2 with matrix which is this one, 1, 2, 3, 4. So what does it mean? So this means that t of the first standard basis is equal to 1, 2, and t of the second basis vector is equal to 3, 4. Now, what will be the pre-image of this parallelogram here? So what will happen here is we take the 1 by 1 squared, right? So because here we have E1 and here we have E2, right? And this 1 by 1 squared, well, E1 gets mapped to vector 1, 2, and E2 gets mapped to this vector. And so what happens is that this square gets mapped to this parallelogram. So we get the following principle. So if a linear transformation T from Rn to Rn has matrix A, then T changes volumes of regions by a factor of absolute value of the determinant of A. So here we have that this unit squared has area 1 and its image has area 2, which is the absolute value of the determinant. And in fact, this applies not only to the unit square, but if we take any region in R2 and find its image under the transformation T, so this linear transformation, then the change in the area will be given by absolute value of the determinant. And this agrees with our formula for the determinant of the product. So now if we have two transformations, T and S, from Rn to Rn, then so T changes volume by a factor of absolute value of determinant of A, and S changes volume by a factor which is determinant of B. And then T composition with S changes volume by factor which is absolute value of determinant of the product A times B. But by our formula, this is equal to absolute value of determinant of A times absolute value of determinant of B. And so which makes sense. So if we have a sequence of two transformations, and we know that the first transformation changes the volume by a certain factor, and the second transformation changes the volume by another factor, then the composition will change volume by the product of these two factors, and which is in agreement with our formula for the determinant of the product. This explains the geometric meaning of the absolute value of the determinant, well, in case when we work over real numbers. But how about the sign of the determinant? Is there a geometric meaning to that? And it turns out that the sign of the determinant also has a deep geometric interpretation. The sign of the determinant gives rise to a geometric notion which is called orientation of a basis. Here we start with the following result. Let A be an n by n square matrix. Then columns of A form a basis of Fn if and only if determinant of A is not equal to 0. So now if we have a basis, so V1 through Vn of Rn, so then to this we can associate matrix A, and to this matrix we can associate determinant of A. So with each basis of Rn we can associate the determinant of A. We call basis of Rn, so V1 Vn, positively oriented if determinant of A is positive, and negatively oriented if determinant of A is negative. And determinant of A cannot be 0 because we have a basis. Now we see that the set of all possible bases of Rn splits into two classes. So there are positively oriented bases and negatively oriented bases. Now let us think, what does it mean geometrically? Here I have chosen three bases on R2. And I denote the first basis vector as red and the second basis vector as blue. Now, the question is, can I deform this basis into one of these two bases? But what I want to do is I want to keep the basis property during my deformation. So this means that I'm allowed to move vectors, but I'm not allowed to make these two vectors linearly dependent. So this means that I'm not allowed to make these two vectors proportional. And then we can see that we can deform this pair of vectors into this pair of vectors by moving red vector into red and blue vector into blue. So this means that we can continuously deform these bases into these bases by preserving linear independence. But it is not possible to transform continuously these bases into these bases, moving blue to blue and red to red, in such a way that we preserve linear independence. At some point, during this deformation, we will have to cross these two lines, and so the basis property will be violated. What this means is that these two bases have the same orientation, and these two bases have opposite orientation. If we have two positively oriented bases, so this means that we can continuously transform one basis into the second basis by always preserving linear independence. But if we have a positively oriented basis and a negatively oriented basis, then we cannot deform the first basis into the second, keeping the linear independence property. And the reason for this is just we can watch the value of the determinant. So when we do continuous deformation, then determinant will change continuously. And we start with the determinant of the first basis and we end up with determinant of the second basis. But if we have a continuous function that switches sign from positive to negative, this means that at some point this function must become zero. And if a determinant of a square matrix becomes zero, so then this tells us that the columns of this matrix will become linearly dependent. So this means that the basis property will be violated along this deformation. A typical linear transformation that switches orientation of a basis is the mirror reflection. So in this picture, one basis is the mirror image of the other, and we can see that these two bases will have opposite orientations. The notion of orientation of a basis leads to the geometric concept of orientability of a surface. A surface is called orientable if we draw a little basis at any point of this surface and then start moving these bases along the surface. And suppose we go around this surface and come back. And when we come back, our bases may change because of deformations along the way. But if we always come back with the basis of the same orientation than the basis we started with, such a surface is called orientable. If we can travel along this surface and come back with the basis that changed its orientation, then such a surface is called non-orientable. As an example of a non-orientable surface, we can look at Möbius strip. So how can we make a Möbius strip? So we take a strip of paper and so we fold it, but we fold it with a twist, like this, right? So this surface that we get is called the Möbius strip. And so here I have drawn a basis on the surface of this strip, right? And if we watch this basis, right, so on the unfolded strip, so this basis goes in the same direction. But if we make a Möbius strip and we trace this basis, then we see that, well, so here the red vector points up, but when it comes on the other side, so we see that here red vector points down. So what we see is that if we start with this basis here and travel along the Möbius strip, then we come back to the same point with the opposite orientation of the basis. And this tells us that the Möbius strip surface is not orientable. Our current understanding of the universe is that the universe has a finite volume. And this means that our universe is not R3, but something else. So it could be some three-dimensional object, or four-dimensional if we count time, which is somehow wrapped up and self-enclosed. And so we want to understand the topology of this object, and we still don't know what it is. And one of the questions that we don't have an answer for is whether our universe is orientable or not. And if our universe were not orientable, then we could take a space flight across the universe and come back possibly from the other side of the universe. And if the universe is non-orientable, then we could come back as mirror flips of ourselves, right? So we'll have heart not on the left, but on the right. So far, we have no evidence that this would be possible. So there is no evidence for our universe to be non-orientable. But still, we don't have a scientific confirmation that our universe is in fact orientable.